Yep, that's working. All right, so we can go ahead and get started. Okay. Here, 7.7, we left off on integration over infinite integrals. Move this up the way. There we go. Okay. So let's say, for example, if we wanted to evaluate the integral from 1 to infinity of 1 over x squared with respect to x. Okay. So if you remember, the integral from 1 to infinity of 1 over x squared with respect to x, we have to rewrite that one as the limit as t approaches infinity of the integral from 1 to t. So we just replace that infinity with any, I get you, they usually call those dummy variables, but any variable at all. And as that variable approaches infinity of 1 over x squared with respect to x. So now we can go ahead and integrate this part. So that's the limit as t approaches infinity. And I'll do the integration kind of on the side. Remember, the integral of 1 over x squared with respect to x, we could just rewrite that as the integral of x to the negative 2 power with respect to x. Okay. So that's equal to x to the power of negative 2 plus 1 divided by negative 2 plus 1, which is x to the power of negative 1 over negative 1, which is negative 1 over x. And plus c. We don't need the plus c because we have a definite integral here. That's the limit of 1 over x from x equals 1 to t. So if we go ahead and apply the fundamental theorem, we have the limit as t approaches infinity of 1 over t minus 1 over 1. Oh, forgot my negative. Sorry about that. So it should be negative 1 over t minus negative 1 over 1. Okay. So if we apply the limit to both of those terms, that's the limit as t approaches infinity of negative 1 over t. Or if you want, you can factor the negative out to the front and just have it 1 over t. Completely up to you. Here we go. And that minus negative becomes a plus the limit of 1 as t approaches infinity. Okay. So we know that the limit of a constant divided by a number that's getting bigger and bigger and bigger has a limit of 0. So this limit is just 0. Plus, we know the limit of a constant is just 1. I mean, the limit of a constant is that constant. And in this case, it's 1. So the limit of 1 is just 1. So that integral is equal to 1. Okay? So we know that the limit exists and that limit is a finite real number. So we know that this integral is convergent. So the limit exists and is a finite real number. So the integral from 1 to infinity of 1 over x squared with respect to x is convergent. And remember, if your limit is positive infinity, negative infinity, or in any way doesn't exist, then it's divergent. Excuse me. All right. So let's say, for example, we wanted to evaluate the integral from 7 to infinity, 2 divided by x squared plus 49 with respect to x. Okay. So for this one, there were two formulas that you're going to want to remember for this particular problem. You have the integral from a constant to infinity. So that's the integral from a to infinity of f of x with respect to x is equal to the limit of the integral from a to t as t approaches infinity of f of x with respect to x. And you want to remember that the integral of du divided by u squared plus a squared, that looks a little too much like a 9. Let me rewrite that one. Is equal to 1 over a times the tangent inverse of u over a plus c. Bless you. So we know that that integral from 7 to infinity of 2 divided by x squared plus 49 with respect to x. We can get that 2 and just factor it right out to the front. So 2, and this integral, we can rewrite that as the limit as t approaches infinity of the integral from 1 to t of dx. We can get that dx and move it right up top. You don't have to, but it helps to put it in the right form. Divided by, and instead of x squared plus 49, we're going to say x squared plus 7 squared. Because now it fits into our integral that results in an inverse trig function. So if you match these up, we see that our u is equal to x. And again, sometimes they might try and trick you and say a squared plus u squared. So they may put this as 49 plus x squared. Your u is still going to be x. Because your constant is always going to be your a. Okay, so u is equal to x, which means the derivative of u is equal to the derivative of x. And we know that our constant a is equal to 7. So we know that this is going to equal 2. And I always like to just plug in my used a's and du's just to make sure everything is where it's supposed to be. So you have the limit as t approaches infinity of dx, which is equal to du. So we're going to go ahead and replace that dx with du. That's the integral. Oh, I put 1. It should have been from 7 to t. I put 1 out of habit. Okay, so the integral from 7 to t, that dx we replace with du, divided by that x squared. Well, u is equal to x, so that's just u squared, plus 7 squared, that's our a squared, so we know that this integral here, we can replace that with 1 over a times tangent inverse of u over a plus c. So that's just equal to 2 times the limit as t approaches infinity. And this entire integral we replace with 1 over a times tangent inverse of u over a. And we don't need the plus c because this is a definite integral, so that's just from 7 to t. So now from here, we just plug in, and again, you could have just gone right to plugging in your a's and u's. I just like to go step by step. So remember, the way I show you it is you'll probably develop your own shortcut, which you should, because I always show the long, drawn-out way. But if you just plug in your u's and your a's, that's 2 times the limit as t approaches infinity of 1 over a. And in this case, remember, matching it up, your a is equal to 7. Oh, there you go. So that's 1 over 7 times the tangent inverse of u over a, so that's x over 7, from t equals 7, from x equals 7 to t. Okay, so now we go ahead and apply the fundamental theorem. Okay, so first thing we're going to do is just go ahead and combine the 2 times 1 over 7 just to get that out the way. And move this over a little bit so we don't run out of room. So 2 divided by 7 times the limit as t approaches infinity. Plug in our upper bound, which is x is equal to t. So that's tangent inverse of t over 7 minus our lower bound, so that's tangent inverse of 7 over 7. We're just tangent inverse of 1. So we know that tangent inverse of 7 over 7 is pi over 4. Okay, and we know that because if we work that out, we know that's tangent inverse of 1. So let's say tangent inverse of 1, we let that equal theta. Oh, running out of room. And make that a little further over so I can have a little more room to write. I thought I gave myself enough space, but I didn't. So tangent inverse of 1 is equal to theta. Okay. So if we apply tangent to both sides, we know tangent of theta is equal to tangent of tangent inverse of 1, where we know the tangent and tangent inverse cancels out. So tangent of theta is equal to 1. Or you could say 1 is equal to tangent of theta. Completely up to you. Okay. So we know that the range of tangent inverse is between negative pi over 2 and pi over 2. So we have to pick a value of theta between negative pi over 2 and pi over 2 that equals 1. So since the range of tangent inverse is negative pi over 2 to pi over 2, the only value between negative pi over 2 and pi over 2 that will make tangent of theta is equal to 1 would be pi over 4. So theta is equal to pi over 4. So that tangent inverse of 1 is just pi over 4. Okay. And we know that from the graph of tangent inverse, if we distribute that limit, then that gives us 2 over 7 times the limit as t approaches infinity. Tangent inverse of t over 7 minus, there we go. Oh, forgot my limit. And I'll just factor out that 2 over 7 still, just to keep from having to rewrite it over and over. So 2 over 7 times the limit of pi over 4. Forgot we already solved that one. As t approaches infinity. So we know here that because that limit of tangent inverse is between negative pi over 2 and pi over 2, we know that as infinity divided by 7 is just infinity. But as you get closer and closer, and it just keeps growing and growing and growing, if you remember the graph, that just means that your tangent inverse just gets closer and closer and closer to pi over 2. Because it kind of looks like this is your x-axis, this is your y-axis, this is your pi over 2, and this is your negative pi over 2. Your tangent inverse function kind of looks like this, give or take. So as your value gets closer and closer to infinity, it just gets closer and closer to pi over 2 without actually equaling pi over 2. So we know this will give us 2 over 7 times pi over 2. I'll leave a little bit of space after that, minus the limit of a constant is just that constant. So that's limit is pi over 4. So to add these two together, we need a common denominator. So we multiply this one by 2 over 2. So that gives us 2 over 7 times 2 pi minus pi is just pi. Nope, not minus, times. Over 4. Which gives us 2 pi over 28, which simplifies to pi over 14. Okay, so because the integral equals a real number, we know it's convergent. Excuse me. All right, any questions on that one? All right. All right. Okay, so what if we wanted to evaluate the integral? Okay, so the integral from 3 to infinity of e to the power of 5x with respect to x. Okay. So again, we know that we have the integral from a constant to infinity, some function f of x with respect to x, is equal to the limit as t approaches infinity of the integral from that constant to t of f of x with respect to x. Okay, so that means that our integral from 3 to infinity of e to the power of 5x with respect to x, we're going to rewrite that as the limit as t approaches infinity of the integral from 3 to t of e to the power of 5x with respect to x. Okay, so now we can go ahead and integrate this part. So that's the limit as t approaches infinity of the integral of e to the power of 5x is 1 over 5 times e to the power of 5x. That's from x is equal to 3 to t. And that 1/5, we're going to go ahead and just factor that right out to the front. Times the limit as t approaches infinity. And now we're going to go ahead and just apply the fundamental theorem. So we plug in our upper bound. So it's e to the power of 5 times t minus e to the power of 5 times 3. So if we simplify it just a little bit, so 1/5 times the limit as t approaches infinity of e to the power of 5t minus e to the 15th power. Or you can solve it like this, or you can distribute your limit to both terms. Again, that's just a personal choice. So 1/5 times the limit e to the power of 5t as t approaches infinity minus the limit as t approaches infinity of e to the power of 15. Okay. Well, we know if we look at the graph of e to the power of x, or you can say e to the power of t, completely up to you. You know, that graph kind of looks like that, and it keeps on going and going and going. So if you make that, like I said, we'll make that t instead of x, so it doesn't matter. So let's say e to the power of t. Just to keep everything nice and familiar. There we go, e to the power of t. So if you make that e to the power of 5 times t, as t gets bigger and bigger and bigger, then that just approaches infinity. That's just 1/5 times infinity minus, and the limit of e to the 15th power is still e to the 15th power because that's a constant. But it doesn't matter because infinity minus anything is still going to be infinity. So again, we could see that this limit is not a finite real number, so we know that the integral is divergent. It's not a finite real number. So we know that the integral from 3 to infinity e to the power of 5x with respect to x is divergent. And clean up that g a little bit there. And again, that's just in case they ask. Sometimes they do. They'll ask, is it convergent or divergent? All right. Any questions on that one? All right. Anyone still writing? Okay. Okay. So now let's suppose that we have some function f. And it is continuous on a finite positive interval. And that's from a to some value b, x equals b, but not including b. So it has a vertical asymptote. Uh-oh. At B. Okay, so what if we let R represent the unbounded region under the function to the right of x equal A and to the left of our vertical asymptote B? Be the unbounded region under our function f of x, or you can say the graph of f, just to be a little more specific, under the graph of f, because we don't know if it's f of x. So we'll just say of our function f, above the x-axis, and between x equals A and x equals B. Okay, so just to show you the difference between the two, this is what we went over first. So if you have your graph, and again, let's say this function kind of goes from here and it keeps on getting closer and closer and closer to x, or the x-axis, without actually crossing it. And that's between some value x equals A. And this value t here just keeps getting further and further away towards infinity. Now this infinite integral they call this one type 1. Okay. Now because that t was just getting closer and closer to infinity and it's just never stopping, it had a horizontal infinite direction. Or had an indefinite horizontal direction. And because of that, we knew that if we had our integral from a to infinity of f of x with respect to x, we could rewrite that as the limit as t approaches infinity of the integral from a to t of f of x with respect to x. Now this definition here, this is type 2. That's what this one's describing. Well, not just that particular point, but the whole thing. So I'll kind of make that represent the whole thing. And what this one is saying is that if you take your XY axis, okay, and let's say you have some x equals a to x equals b interval. Or in this case, b is a vertical asymptote. So we know that x cannot equal b for whatever reason. So that's our vertical asymptote, which is our vertical line. So our graph can look something like this, where it'll never cross that x is equal to b. So we know it's between x equals a, and it's approaching b from the left. It'll never equal b. It's just approaching b from the left. Okay, so this whole region that we will call R, you can find that that's the integral from a to b of f of x with respect to x. But because, again, it cannot equal b, we're just going to rewrite that as the limit as our value t just gets closer and closer to b. So t approaches b from the left of the integral from a to t of f of x with respect to x. Okay. Now, because this t is going or having infinity as t is approaching infinity, this one has a vertical infinity, or vertical infinite direction, to be a little more specific. An infinite vertical direction, where this one had an infinite horizontal direction. This t is just going to keep going and going and going horizontally, and this infinity is going and going and going vertically. Same general idea, but you do have to kind of tweak the formula a little bit. All right, anyone still writing? Okay. Okay, so these are your definitions of improper integrals that are all considered type 2. There's the one we just showed. We'll call that one A. It says that if f is continuous, so if our function f is continuous, on some interval from A to B, where it's discontinuous at B, where B is your vertical asymptote, then we know that the integral from A to B of f of x with respect to x is equal to the limit as t approaches B from the left of the integral from A to t of f of x with respect to x. Okay, so that was the one we just showed, all of the detail and ideas behind it. Okay, but this all depends on the limit actually existing. So it's provided the finite limit exists. Now for B, imagine the very same graph, but instead the vertical asymptote is A. So the graph is just going further and further and further and up on the direction of A, where it's really just approaching A from the right. It's getting closer and closer to A from the right. So here we say that if F is continuous, but in this case, from A to B, it can include B but not A. And discontinuous at A. Okay, which means your T is now approaching A from the right because A is now the one going higher and higher and higher. And we know that the integral from A to B, f of x with respect to x, is equal to the limit as t approaches A from the right of the integral from t to b of f of x with respect to x. So kind of separate those formulas a little bit. Okay, so what if your graph is discontinuous at some value C that happens to be an element or in the middle of A and B or somewhere in between A and B? Okay, so what if our function f is discontinuous at some value C? Well, we know that C is somewhere between A and B. And we know that the integral from A to C of our function and the integral from C to B of our function are both convergent. which means if you find their integral, it's a finite real number. Okay, now if that's the case, then we know that we can rewrite the integral from a to b of f of x with respect to x is equal to the integral from a to c of our function f of x with respect to x plus the integral from c to b of our function f of x with respect to x. Okay, and just remember that convergent means that the finite limit exists and divergent just means the finite limit does not exist. And that's just a little side note, kind of a reminder. All right, anyone still writing? Oh, still writing. All set. All right. Okay, so let's say, for example, if we wanted to evaluate the integral from -6 to 1 over the square root of 1 minus x with respect to x. Okay, so with this one, the first thing you notice is that if you plug in x is equal to 1, it would be undefined. It would give you a denominator of 0. Okay, so we know that just by that little fact, f of x is equal to 1 over the square root of 1 minus x. It is only continuous for x equals -6, because you can plug in -6 and be just fine. But 1 you cannot, so you have to have that parenthesis. Okay. So if you're ever wondering which formula you'd use, always kind of write it out like that and see which number have the parentheses. So this is your A, and this is your B. So you can't equal B, so that means you have to find the limit as you're approaching B from the left. So if you're approaching B from the left, we know that we're going to use the integral from A to B of f of x with respect to x is equal to the limit as t approaches B from the left. Of the integral from a to t of f of x with respect to x. Most of the time, the hardest part is getting started. So just doing that part and finding out, okay, if it's approaching B from the from the left, and it can't equal B, then you know this is the one you're going to use. Which means we can rewrite our integral from -6 to 1 of 1 over the square root of 1 minus x with respect to x. We could rewrite that as the limit as t approaches 1 from the left. Of the integral from -6 to t of 1 divided by the square root of 1 minus x with respect to x. And that one is a little bigger than I want it to be. There we go. Okay, so we can go ahead and integrate our 1 over 1 square root of 1 minus x. And we'll do that on the side just to kind of save space. Okay, so we know that we can write our 1 over the square root of 1 minus x. We can rewrite that as 1 minus x to the negative 1/2 power. So if we let u equal 1 minus x, okay, so if we take our derivative of u, that's going to equal -1 dx. So if we divide or multiply both sides by -1, just to save a step, we know our negative du is equal to dx. So this integral is just negative u to the negative 1/2 power du. And I'll just rewrite this as an integral. And move that arrow out the way a little bit so you can see the negative sign. Here we go. Make sure it's as clear as possible. Okay, so that's going to equal negative. And the integral of u to the negative 1/2 is u to the negative 1/2 plus 1, which is positive 1/2. So u to the positive 1/2 over positive 1/2. And I'll leave a little bit of space after that one. And I'll put the plus c, but we don't need it because it's a definite integral, but I'll put the plus c anyway. Okay, so we want to get rid of that 1/2 in the denominator, so we multiply this by 2 over 2. We're at 1/2 times 2 is 1, so those two cancel each other out. And that 2, we can go ahead and factor that out to the front. So that -1 times 2, that gives us -2. Times u to the 1/2 power, well, we can go ahead and just replace that u with 1 minus x. So that's 1 minus x to the 1/2 power, or just square root of 1 minus x. Move that over a little bit. So that's going to equal that -2, we can go ahead and factor that out to the front. So -2 times the limit as t approaches 1 from the left, and that just becomes the square root of 1 minus x. And that's from -6 to t. So now we can go ahead and apply the fundamental theorem and move that equal sign over a little bit. We have that -2 times the limit as t approaches, why do I keep putting t? T approaches 1 from the left. If we plug in our t, that's the square root of 1 minus t minus the square root of 1 minus -6. Okay, so if we go ahead and distribute that limit to both terms, we have -2 times the limit of the square root of 1 minus t as t approaches 1 from the left minus the limit, square root of 1 minus -6 is just the square root of 7 as t approaches 1 from the left. Okay. So if you're approaching 1 from the left, you might as well say you're approaching 0.5, 0.9, 0.99, 0.999. Basically, it's getting bigger and bigger and bigger without actually hitting 1. Or if you want, it's just easier because sometimes you don't want to visualize it. You put 0 and 1. So if you're approaching 1 from the left, it's just getting bigger and bigger and bigger. So if this is just getting bigger, 0.9, 0.99, 0.999, et cetera, and so on, then this limit is just really getting closer and closer to 0. Because as this number gets bigger and closer to 1, this just keeps getting smaller and smaller and smaller, so this limit approaches 0. And this limit of a constant is just going to be that constant. So this limit is just going to be square root of 7. So that's -2 times 0 minus square root of 7, which you could just rewrite it as -2 times negative square root of 7, which is just 2 square root of 7. All right, any questions on that one? All right. Okay, so now we're going to look at the comparison theorem for improper integrals. Okay, so let's say that suppose that we have two functions f and g. And those two functions are continuous over some open interval from a to b. And we know over that interval, we know that g of x is less than or equal to f of x. And both are greater than 0. For x is greater than or equal to a. So if those stipulations are true, we know that if the integral from a to infinity of f of x with respect to x is convergent, then the integral from a to infinity of g of x with respect to x is convergent. Okay, so visually, all that means that if we have some xy axis, let's say this is our function f of x. And we're looking at some interval from, or really just x is greater than a. So let's say this is our a. So we're looking just at this direction. X is greater than a. So for some function g of x, we'll say this is our g of x function coming up. It doesn't matter what it's doing before that. Before a, it can go anywhere it likes. It can go above f of x, doesn't matter. But once it hits a, we know that it's always going to be below f of x. So if f of x converges to one specific limit, then we know that g of x converges to one specific limit. Kind of a little tweak to the squeeze theorem. Okay. And we also know that if those stipulations are true, if we know the integral from a to infinity of g of x with respect to x is divergent, then we know that the integral from a to infinity of f of x with respect to x is also divergent. Okay, well, all that means is that you take your x and y axis, and again, you have some value a. Let's say if we find the limit of g of x and we know that g of x is divergent, which means it keeps going up and up and up. There's no limit. There's no finite limit. So this is your g of x. Okay. Well, if g of x is always less than f of x, which is the stipulation right here, then we know once you get past x is equal to a, that f of x is always going to be above your g of x. So it's going to kind of look like that. So if that g of x keeps on going to infinity, then that f of x is going to keep on going to infinity. It's going to be divergent. Okay. Now the tricky part is if g of x is convergent. Then this theorem means absolutely nothing. It is inconclusive. Because it really doesn't tell us whether f of x is convergent or divergent. And to kind of visualize that a little bit. Okay. So we know that, let's say if we have g of x converges to some limit that we'll call L. Okay, so this is your g of x. Okay. Well, your f of x could converge to that same limit. That f of x could converge to infinity. We have absolutely no idea. Even though it meets all the stipulations, doesn't matter if g of x is convergent. We still have no clue which one it is. Okay. So as long as g of x is not convergent, you can figure it out. At least that's if we figure it's convergent on its own. Okay, so we can't use g of x to find out whether or not f of x is convergent, but we can use f of x to find out if g of x is convergent. That's the little tricky part of it. All right, anyone still writing? All right. So let's say, for example, if you want to determine whether the comparison theorem, they may say comparison theorem or comparison test, same thing, proves that the integral from 9 to infinity of e to the power of x plus 4 divided by the cube root of x plus 2 with respect to x converges or diverges when comparing it to the integral from 9 to infinity of 1 over the cube root of x with respect to x? Or will it be inconclusive? Do, 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 do. So with these two, the first thing I would recommend doing is graphing the two functions. And you can do that using Desmos or your graphing calculator. To see which is greater over the interval from 9 to infinity. Okay. So if you graph them, you will see that 1 divided by the cube root of x is less than or equal to e to the power of x plus 4 over the cube root of x plus 2. Over the interval from 9 to infinity. Oh, got my greater. There we go. Okay, so this is your g of x, and this is your f of x. Okay, so if we can prove this g of x is divergent, then we know this f of x is divergent. But if this g of x is convergent, then we have no idea what this is, and we'd have to find it using another test. So this would be inconclusive. So now we find the integral of our g of x. Okay, so the integral from 9 to infinity of 1 over the cube root of x with respect to x. We're going to rewrite that as the limit as t approaches infinity of the integral from 9 to t. And instead of 1 over the cube root of x, we're just going to rewrite it as x to the negative 1/3 power. So we can use the, not the power rule. I guess you call it the power rule. I think that's the name of it. Can't remember. Okay, so we know that the integral of x to the negative 1/3 power, we can work it out here on the side. With respect to x, you can get that with x to the negative 1/3 plus 1, which is 2/3, divided by 2/3. And again, you can put your plus c, but because it's a definite integral, we won't be actually using that plus c. So if we multiply the numerator and denominator by the reciprocal of the denominator, so it's 3 over 2 divided by, kind of ran into the plus sign a little bit. Actually, it's giving me a chance to just move this over some. Oops. So multiply this by 3 over 2 over 3 over 2. These two give you 6 divided by 6, which is just 1, so they cancel each other out. And that 3 over 2, we can just bring it right up here. So 3 over 2 x to the 2/3 power plus c. So we know that this integral gives us the limit as t approaches infinity of 3 over 2, and we could have factored that 3 over 2. We'll do that at the end. So 3 over 2 times x to the 2/3 power. That's from t equals 9, x equals 9 to t. So now we can apply the fundamental theorem. So we know the limit as t approaches infinity. We plug in our t, that's 3/2 times t to the 2/3 power minus 3/2 times 9 to the 2/3 power. Okay, so if you wanted to, you could rewrite this as the cube root of t squared. It doesn't matter because as t gets bigger and bigger and bigger, that cube root of t squared is just going to get bigger and bigger and bigger. So we know that this limit is going to be infinity, which means it doesn't matter what this is because this is just some value that's constant. Infinity is still going to bypass it. So infinity minus this number doesn't matter. So we know this limit is going to be infinity, which means it diverges, or g of x diverges. So we know from definition A that if g of x diverges and it's less than your f of x, then f of x diverges. So since 1 over the cube root of x is less than or equal to e to the power of x plus 4 over the cube root of x plus 2, and that 1 over the cube root of x diverges, then your f of x, or your integral from 9 to infinity of e to the power of x plus 4 over the cube root of x plus 2 also diverges. All right, any questions on that one? All right, anyone still writing? Okay. Okay, so let's say, for example, we want to determine whether the comparison theorem will prove whether the integral, say the integral from 2 to infinity. Oh, I know exactly how that 8 slipped in there. 2 to infinity of 6 divided by 2x to the 3rd power plus 4 with respect to x converges, diverges, or is inconclusive. When compared to the integral from 2 to infinity of 1 over x to the 3rd power with respect to x. Okay. So again, first thing you want to do is just graph both of your functions to see which one is greater than the other over the interval, in this case from 2 to infinity. Okay, so we know that graphing both functions shows that we know that 1 over x to the third power is less than or equal to 6 divided by 2x to the third power plus 4. And that's just over the interval from 2 to infinity. Okay. Again, before that, we do not care, at least for this particular problem. Okay. So in this case, your g of x is less than or equal to your f of x. Okay, so if we take our integral from 2 to infinity, and make that infinity look a little bit better than that. There we go. Of 1 over x to the third power with respect to x. We can rewrite that as the limit as t approaches infinity of the integral from 2 to t. And instead of 1 over x to the third power, we're just going to rewrite that as x to the negative 3 power with respect to x. And make that negative 3 a little bit clearer. There we go. And that 1 over x to the third, make that a little bit better looking than what it is. There we go. Okay, so if we integrate x to the negative 3 power, that gives us the limit as t approaches infinity. And this integral right here becomes x to the negative 3 plus 1 over negative 3 plus 1. So that's x to the negative 2 power over negative 2, which gives us negative 1 over 2 to the 2 times x to the negative 2, which is just 2 over x squared. And that's from 2 to infinity. 2 to t. So now we go ahead and apply the fundamental theorem. Move that over to the left a little bit so we have enough room. So the limit as t approaches infinity. So we go ahead and plug in our upper bound. So that's negative 1 over 2 times t squared minus negative 1 divided by 2 times 2 squared. Okay, so we have the limit. Oh, actually, we don't even have to write this anymore. We can just go ahead and solve it since we're running out of room a little bit. We take the limit of negative 1 over 2 times t squared. As t gets bigger and bigger and bigger and bigger and bigger, this value as a whole gets smaller and smaller and smaller and smaller and smaller. So we know that this limit just approaches 0. Whenever you have a constant divided by a number getting smaller and smaller and smaller, bigger and bigger and bigger. Minus negative, that just becomes minus negative 1 over 2 squared, which is 4, times 2 is 8. So that minus negative is just plus. So that's just 1 over 8. So this lets us know that the integral from 2 to infinity of 1 over x to the third power with respect to x converges to that finite real number. Okay, which means it's absolutely no help in telling us whether or not our original integral converges or diverges. Okay, so since the integral from 2 to infinity of 1 over x to the third power with respect to x converges, and we know that 1 over x to the third power is less than or equal to 6 divided by 2x to the third power plus 4, the results are inconclusive. And go ahead and just draw a little separator box around that one. Okay. Not saying there's no way to find out, because we will look at other tests and theorems in chapter 9, but just using this one test, we can't tell. All right, any questions on that one? All right. So that's it for 1.7. So we're going to go ahead, not 1.7, 7.7. So we're going to go ahead and start on 8.1. Organize these now. Oh, I'm sorry. Anyone still writing? Okay. There we go. All right, so section 8.1. We're going to kind of have a brief introduction to differential equations. And these are just general solutions. To differential equations. I'll just put it down here. A differential equation is really just an equation with one or more derivatives involved of an unknown variable. A differential equation. And sometimes you'll just see DE instead of writing out differential equation each and every time. Is an equation involving one or more derivatives as an unknown function. Okay. Now the order of a differential equation is pretty similar to the order of, like I say, a polynomial or something like that. But in this case, you're just looking for the highest derivative in that particular equation. So the order of a differential equation. You'll probably hear diff EQ more than you hear DE. So, okay, so we know that the order of a differential equation is the order of the highest derivative. Clean that up a little bit. There we go. Okay, so let's say if you have derivative of y with respect to x minus 2y is equal to 0. Well, the highest derivative is the first derivative. This is just not the equation, the variable y. So we know this is a first order. Okay. Or what if you have the second derivative of y with respect to x minus 4 dy dx plus 9y is equal to 0. Well, we know the highest is a second order derivative. I mean, not second order, the second derivative, which means this is a second order. And in some cases, they won't write it in that form. They just may write y and just put the third derivative like that. So let's say plus 5 times the second derivative plus 7 times the first derivative minus 3y is equal to 5. Okay. So again, we can see the highest is the third derivative. So we know this is a third order differential equation. Excuse me. Okay. Also, you might see some where you have, let's say, sine of 3x. Excuse me. Oh, let's say is equal to, kind of switch it up a little bit. Sine of 3x times the third derivative of y plus sine of 5x times the fourth derivative. Remember, anything above third derivative, they'll put it in parentheses as an exponent. Okay, so we know that this is a fourth order differential equation. All right, any questions on that one? Okay. All right. Let's look for solutions to differential equations. Okay, so we know that a function y is equal to y of x is a solution to a differential equation on an open interval if the equation satisfies identically on an interval and identically on the interval when y and its derivative and it could be more than one derivative, so I'll say derivatives with s in parentheses, are substituted in the equation. Oh, that end looks a little bit messy. There we go. Okay, so let's say, for example, we want to determine if y is equal to e to the power of 2x is a solution of the differential equation dy dx minus y equals e to the power of 2x on the interval from negative infinity to infinity. And honestly, this looks worse than what it really is. Solving it isn't too bad as far as differential equations go. Okay, so we know that y is equal to e to the power of 2x. That's our given. So our differential equation only goes up to dy dx, so we want to find that. So our dy dx is equal to 2 times e to the power of 2x. So all you have to do is have your dy dx minus y equals e to the power of 2x, and just substitute your dy dx. You're going to plug in 2 times e to the power of 2x minus your y, which is e to the power of 2x. This is equal to e to the power of 2x. So 2 times e to the power of 2x minus, and you can think of it as 1 times e to the power of 2x. 2 minus 1 is just 1, so it's 1 e to the power of 2x, or e to the power of 2x is equal to e to the power of 2x, which is true. Okay. Now the thing about it is, yes, this is a solution, but it is very possible that it's not the only solution. But possibly not the only solution. Okay, so let's say instead of letting y equal e to the power of 2x, move that over, there we go. So what if we let y equal e to the power of 2x plus some constant times e to the power of x, where c is equal to constant. Okay, so that means our derivative of y with respect to x is equal to the derivative of e to the power of 2x, which is 2 times e to the power of 2x, plus some constant times e to the power of x, which is still some constant times the derivative of e to the power of x. Make that e a little bit neater. So if we plug those in, we know our dy dx minus y is equal to e to the power of 2x. That's what we're trying to prove. So your dy dx, we're just going to replace that with 2 times e to the power of 2x plus c times e to the power of x. 2 e to the power of 2x plus c times e to the power of x. minus y, well, that y, we're going to replace that with e to the power of 2x plus c times e to the power of x. We want to know if that equals e to the power 2x. So if we distribute that -1, we have 2 times e to the power of 2x plus c times e to the power of x minus e to the power of 2x minus c times e to the power of x. We want to know if that equals e to the power of 2x. So we can see that our constant times e to the power of x, we have two opposites, so those two disappear. So we still have 2 times e to the power of 2x minus e to the power of 2x. So on the left side, we have e to the power of 2x. And on the right side, we have e to the power of 2x, which is true. So you can have more than one solution. All right. So let's say, for example, if we wanted to know is y equals 5 times the square root of x plus 2, a solution to the differential equation -2y prime is equal to 15 square root of x minus 3y plus 6 minus 5 over the square root of x. Just don't really need it in any particular form. Okay. So again, we know that y is equal to 5 times square root of x, but I'll rewrite that as x to the 1/2 power only because it's easier to differentiate, plus 2. Okay, or you can write it the original way, doesn't matter, completely up to you. 5 square root of x plus 2. Now when I'm differentiating, I'll do it in this form, but when I'm plugging it in, I'll have it in this form, only to cancel out whenever it's necessary. That means your first derivative, or your y prime, is equal to 5 times the derivative of x to the 1/2 power. So we bring down the 1/2. So we have 5 over 2 times x to the power of 1/2 minus 1, which is -1/2. Plus the derivative of 2, which is 0. So you can say plus 0 or just leave it blank. Or you can rewrite it as y prime is equal to 5 over 2 times the square root of x. Okay, so that means our negative 2y prime is equal to 15 square root of x minus 3y plus 6 minus 5 over square root of x. We can just substitute. Okay. Another way to do this one, actually, we could substitute, but I think that one might be a little bit longer. Another way to do a problem like this, which might be a little easier depending on the problem, is to separate our derivatives. And then substitute. And that should work on this one. Instead of just plugging in your y primes and all of that. Which, like I said, always works, but you can always helps to know more than one way. Okay, so if we add 5 over square root of x to both sides, actually we can just keep those together and just get rid of the negative 2y prime minus 3y. So we can add, oh, actually we can go ahead and add that to both sides. So we can have 15 square root of x minus 5 over square root of x is equal to negative 2y prime, and add 3y to both sides, plus 3y plus 6, or minus 6. So all we did was separate our x terms and y and derivative terms. So we can have negative 2 times y prime, which is 5 square root of x plus 2. Oh, 5 over 2 square root of x, sorry about that. Plus 3y. So plus 3 times y, which is 5 square root of x plus 2. Minus 6. Okay. So the 2's cancel each other out. So that's negative 5 over square root of x. And if we distribute that 3, plus 15 square root of x plus 6, and we still have that minus 6 right there, where these two cancel each other out. So you have negative 5 over square root of x plus 15x, well, square root of x. Or you can switch those around and just say 15 square root of x minus 5 over square root of x, where these two are equal. So again, this is just an option. If you wanted to, you could have definitely plugged in your first derivative here, your y here, and did it that way. It's completely up to you. Okay, so since they're equal, we know that yes, it is a solution. Oh, bring that up a little bit. Sometimes it just helps to know more than one way to do it. All right, any questions on that one? Okay, anyone still writing? All right. Okay, so let's say, for example, bring that over a little bit. There we go. We want to know is y is equal to -3 e to the power of x plus 3 e to the power of -2x. A solution for 3y minus 2 is equal to -2 times y prime plus 3 times the second derivative of y minus 6 times e to the power of x minus 2 minus 39 e to the power of -2x. So we can tell the highest derivative is the second derivative. So we know it's a second order, so we have to go up to the second derivative. Okay. So we know that y is equal to -3 times e to the power of x plus 3 times e to the power of -2x. That was our given. Okay, now our first derivative is equal to -3 times e to the power of x, since that is the derivative of -3 e to the power of x, plus 3 times the derivative of e to the power of -2x is -2 times e to the power of -2x, which is e to the power of -2x times the derivative of -2x, which is -2. So go ahead and multiply those two just to simplify it. We know that y prime is equal to -3 times e to the power of x minus 6 times e to the power of -2x. And we'll go ahead and draw a little rectangle around that one. Right, so now we have to find the second derivative, which is just the derivative of the first derivative. That's going to be -3 times e to the power of x minus 6 times the derivative of e to the power of -2x, which is -2 times e to the power of -2x. So again, if we go ahead and multiply those two just to simplify it, we know our second derivative is equal to -3 times e to the power of x plus 12 times e to the power of -2x. So we have y, we have our first derivative, and we have our second derivative. Okay, so now we can just go ahead and plug it in. So 3y minus 2 is equal to negative 2 times y prime plus 3 times the second derivative of y minus 6 times e to the power of x minus 2 minus 39 e to the power of negative 2x. So again, you can just plug them right on in, but for me, sometimes it's a little easier because you don't have to go all the way down to the very end if you just separate and substitute. Okay, so just get all of our y terms to one side, all of our x terms to the other. Okay, so if we add 6e to the power of x to both sides and add 39e to the power of negative 2x to both sides, and that gives us 3y prime, well, second double prime, or 3y to the second derivative, minus 2y prime, since we already have that over there, and subtract 3y from both sides, minus 3y. And if we add 2, these two just cancel each other out. So those two just disappear. Okay. So again, doing that to me just relieves some of the work, because all you have to do is plug it in here and see if it matches the left side. Okay. So we know this is just 3. Let me move it over just to make sure I have enough room. I have a tendency to run out of room here. So we want to know if we replace the 3y double prime with 3 times negative 3 e to the power of x plus 12 times e to the power of negative 2x minus 2 times y prime, so 2 times negative 3 e to the power of x minus 6 times e to the power of negative 2x, and still ran out of room. Minus 3y, so minus 3 times negative 3 e to the power of x plus 3 e to the power of negative 2x. Okay, so now we're going to go ahead and distribute the 3 and distribute the negative 2 and distribute the negative 3. We want to see that when we're done, if it equals the left side. So we have negative 9 e to the power of x plus 36 e to the power of negative 2x plus 6 e to the power of x plus 12 e to the power of negative 2x plus 9 e to the power of x minus 9 e to the power of negative 2x. Okay, but we can see negative 9 e to the power of x and 9 e to the power of x, they cancel each other out. Okay, so we have 6 e to the power of x. Okay, and we have 36 e to the power of negative 2x plus 12 e to the power of negative 2x minus 9 e to the power of negative 2x, which gives us 39 e to the power of negative 2x. Make that equal sign a little bit clearer. So we see that these two are equivalent. So we know that it is a solution. So y equals negative 3e to the power of x plus 3e to the power of negative 2x is a solution. So again, there are multiple ways you can do it. So if you don't like this way, you can just plug it in right from here and go that way. Completely okay. All right. Any questions on that one? All right. Anyone still writing? Okay, so what if we want to know is y is equal to negative 4 times cosine of 4x, a solution. For 36y is equal to the second derivative of y. There we go. Okay, so we know that y is equal to negative 4 times cosine 4x. We're going to need to plug that in, so we're going to just go ahead and draw a little rectangle around it. And the first derivative is equal to negative 4 times the derivative of cosine of 4x. Which is 4 times negative sine of 4x. Well, negative and negative is positive, and those two 4s multiplying together, we get y prime is equal to 16 times sine of 4x. And we know that the second derivative is equal to 16 times the derivative of sine of 4x, which is just 4 times cosine of 4x. So we know that the second derivative is equal to 64 times cosine of 4x. So if we have 36y is equal to the second derivative of y, means we have 36 times -4 times cosine of 4x, since that's our y, is equal to 64 times cosine of 4x. Okay, so we multiply those two, we get -144 cosine of 4x is equal to 64 times cosine of 4x, which is false. Bless you. So we know that y is equal to -4 cosine of 4x is not a solution. All right. Any questions on that one? Okay. Now, what if we wanted to find the solution yourself to your first order differential equations? And with that, really, you just have to remember that the integral of a derivative is just equal to the position function. Okay, so if you have the integral of your first derivative, the integral and your derivative cancel each other out. So that's just your position function. Or sometimes they'll put it in the form where you have the integral of your dy dx with respect to x. Still the same thing, your original function. Okay, so let's say, for example, if we wanted to find the general solution to the differential equation y prime is equal to 2x to the third power minus 4x squared. So So if we integrate every term, we know that the integral of your y prime with respect to x is equal to 2 times the integral of x to the third power with respect to x minus 4 times the integral of x squared with respect to x. So again, the integral of your derivative is just your function. So you can just say y is equal to 2 times the derivative of x to the third power, which is x to the fourth power over 4, minus 4 times the derivative of x squared, which is x to the third power over 3. And we'll combine all of those plus c's into just one constant. So that gives us a general solution of y is equal to 2 divided by 4. You can just simplify that to 1/2 x to the fourth power minus 4 divided by 3 times x to the third power plus c. All right. Any questions on that one? Okay. Now, if we're looking for a particular solution that's really similar to the initial value problems from Calc 1. Okay, so let's say if we want to find the particular solution. For the differential equation dy dx is equal to -4 times x to the third power plus 4x. If you're given that y of 2 is equal to -4. Okay, so again, really similar to an initial value problem. So just like before, we go ahead and integrate each term. So we have the integral of your dy dx with respect to x is equal to -4 times the integral of x to the third power with respect to x plus 4 times the integral of x with respect to x. Okay, so again, we know the integral of a derivative cancels each other out, leaving just our position function, but instead of y, we'll call it y of x. You don't have to, but because we have our particular solution that we're looking for, we're just going to make it y of x, since eventually we're going to have to look for y of 2. Okay, so that's equal to -4 times the integral of x to the third power, which is x to the fourth power over 4, plus 4 times the integral of x, which is x squared over 2. And we're going to combine all of our plus c's into one plus c at the end. Okay, so you can see here the 4's cancel each other out. So we know that y of x is equal to negative x to the 4th power plus 4 divided by 2 is 2, so that's plus 2x squared plus c. Okay, so if they didn't give us that y of 2 is equal to negative 4, this would just be our general solution. And we would just stop there. But they did give us this y of 2, so we have to keep going. Okay, so we know that since y of 2 is equal to negative 4, plugging that into our general equation, we know that y of 2 is equal to negative x to the 4th power. So that's negative 2 to the 4th power plus 2 times 2 squared plus c. We know that y of 2 is equal to negative 4. So all of that has to equal negative 4. So we're just going to take this, and this is the only part of it we're going to focus on. We're going to kind of ignore that. Okay, so 2 to the 4th power is 16, and that's negative, so that's negative 16. We have 2 to the 4th squared, which is 4, times 2, which is 8, plus c is equal to negative 4. So if we go ahead and combine those two, that gives us negative 8 plus c is equal to negative 4. So if we add 8 to both sides, that gives us c is equal to negative 4 plus 8, which is just 4. So we get that value of c and plug it into our general solution. So we know that y of x is equal to negative x to the 4th power plus 2x squared. And instead of plus c, we're just going to make that plus 4. And that is our particular solution. All right, any questions on that one? All right, so let's say, for example, oops. Let's say if we want to find a particular solution to the differential equation y prime is equal to negative 4 pi times secant squared pi times x divided by 3. If you're given that y of 3 is equal to 2 pi. Okay, so again, we can go ahead and integrate each term. So the integral of y prime with respect to x is equal to, and we can go ahead and factor out that negative 4 pi just to make things a little easier, times the integral of secant squared of pi x divided by 3 with respect to x. Okay, so now we just have to integrate our secant squared, because on the left side, that's just our y of x. So let's go ahead and integrate our secant squared. I'll do that over here. Okay, so we have the integral of secant squared pi times x divided by 3 with respect to x. Okay, so using u substitution, we're going to let u equals pi over 3 times x. Which means if we find the derivative, our du is equal to pi over 3 dx. So if we multiply both sides by the reciprocal, that means 3 over pi du is equal to dx. So that means we replace dx with 3 pi over du. We can factor out that 3 over pi. Give myself a little more room. So we have 3 over pi times the integral of secant squared of u du. So we know the integral of secant squared is tangent. So that just becomes 3 over pi times tangent of u. And we can use plus c. Replace our u with pi over 3x. So we know that integral is 3 over pi times tangent of pi over 3 times x plus c. Oops, straighten it up a little bit. There we go. So we know this is equal to negative 4 pi. And the integral of secant squared of pi over 3x, we know that is 3 over pi times tangent of pi over 3 times x plus c. All right, we're here, we can see that the pi's cancel each other out. And we can go ahead and multiply the negative 4 times 3. So that means our y of x is equal to negative 12 times tangent of pi over 3 times x plus c. Okay, so again, this is our general function. And it's given that y of 3 is equal to 2 pi. Okay, so since we know that y of 3 is equal to 2 pi, we just plug 3 into our general function. So that gives us y of 3 is equal to negative 12 times tangent of pi over 3 times 3 plus c. And we know that y of 3 is equal to 2 pi. So once again, we're just going to focus on this part. So we have negative 12 times tangent. These 3's cancel out, so that's just tangent of pi plus c is equal to 2 pi. Okay, so we know tangent of pi is equal to 0. And we know that because we know that tangent of pi is just sine of pi divided by cosine of pi. We know that sine of pi is equal to 0 and cosine of pi is equal to 1, which is just 0. So we know that since this is equal to 0, this whole term just disappears. So we know that c is just equal to 2 pi. So we get this, plug it into our general function. So we know that y of x is equal to negative 12 times tangent of pi over 3 times x. And instead of plus c, it's going to be plus 2 pi. And this is our particular function. Like I said, hopefully this looks familiar because it's very, very similar to the initial value problems. All right. Any questions on that one? Okay. So we will go ahead and stop there. We'll start on section 8.3 next time. And again, if you have questions, feel free to ask away. Now we have 8.3 and 8.5, and then we'll have the test. The test is 7.3 to 8.5. All right, you too. Thank you. All right, you too.
on that day.
You too. And let me see what else my freeze that on here. Oh, here we go. Right. Let me see if there are any questions here. Nope. Yes, the review will be posted. So you'll probably have the review posted today or tomorrow. So you should be able to access them then. And the due date will probably be the same as last time, probably make it Friday with a 1-day grace period till Saturday. So hopefully that'll be plenty of time to take it. All right, thank you, Muhammad. You have a good day too.